Hello. Welcome to the Quiet Observatory. My name is Atta. Tonight, we're approaching the most extreme objects in the universe. Places where gravity is so strong that not even light can escape. Places where the very fabric of space-time tears and folds in ways that challenge our understanding of reality. Black holes. The name itself sounds like something from science fiction, doesn't it? A hole in space. A region of darkness so profound that nothing can emerge from it once it crosses a certain boundary. For a long time, black holes were purely theoretical, mathematical curiosities predicted by Einstein's equations, but never observed, never confirmed. Einstein himself didn't believe they could actually exist. The idea seemed too strange, too extreme. But they do exist. We've detected them indirectly through their effects on nearby matter. We've heard them merge, creating gravitational waves that rippled across the universe and rang in our detectors like bells. And in 2019, we photographed one, capturing the shadow of a supermassive black hole at the center of a distant galaxy, exactly where the theory predicted it would be. Tonight, we're going to journey to the edge of understanding. We'll explore how black holes form, what happens at the boundary where nothing can return, and what might lie beyond that point of no return. We'll encounter some of the strangest predictions in all of physics, predictions that have been tested and confirmed, that are now accepted as simple facts about the universe we inhabit. And we'll find ourselves at the frontier, where our best theories, general relativity and quantum mechanics, meet and break down, unable to tell us what happens at the very center, at the singularity, where density becomes infinite and space-time itself ends. Let's begin at the beginning, with the death of a star. Black holes are born from the deaths of massive stars. Stars at least 20 times more massive than our Sun. These stellar giants live fast and die young, burning through their nuclear fuel in just a few million years compared to the Sun's 10 billion year lifespan. During a star's life, it's held in balance. Gravity pulls inward, trying to collapse the star. Nuclear fusion in the core releases energy that creates outward pressure, pushing back against gravity. As long as fusion continues, the star remains stable. But fusion can't last forever. As the star ages, it runs out of hydrogen in its core and begins fusing heavier elements. Helium into carbon, carbon into oxygen, oxygen into silicon. Each stage happens faster than the last. A star might burn hydrogen for millions of years, but it burns silicon for only a few days. Finally, the core produces iron, and iron is the end of the line. Fusing iron doesn't release energy. It absorbs energy. Once a star's core turns to iron, there's no more fuel. Fusion stops. The outward pressure vanishes. And gravity wins. core collapses catastrophically. In less than a second, faster than you can blink, the core implodes. Electrons are crushed into protons, forming neutrons. The core becomes a ball of neutrons compressed to nuclear density, about the density of an atomic nucleus. For stars below a certain mass, roughly 2 to 3 times the mass of the Sun, the collapse stops at this point. The neutron core, supported by neutron degeneracy pressure, stabilizes as a neutron star. These objects are almost impossibly dense. A teaspoon of neutron star material would weigh 1 billion tons on Earth. But for stars above this threshold, the Tolman-Oppenheimer-Volkoff limit, even neutron degeneracy pressure isn't enough. Nothing can stop the collapse. The core continues to compress, smaller and smaller, denser and denser. There's no known force that can halt it. The core passes the point where it becomes smaller than the Schwarzschild radius, the critical size where the escape velocity exceeds the speed of light. At that moment, a black hole is born. The collapse doesn't stop. The matter continues falling inward, compressed to what general relativity predicts is infinite density at a single point, a singularity. But we're getting ahead of ourselves. We'll return to the singularity later. For now, let's focus on what happens to the star's outer layers. The collapse of the core releases an enormous amount of gravitational energy. A shock wave rebounds through the star's outer layers, blowing them off in a supernova explosion so powerful it can briefly outshine an entire galaxy. The explosion scatters heavy elements, carbon, oxygen, iron, gold, uranium, into space, seeding the interstellar medium with the raw materials for future planets and life. Every atom in your body, heavier than hydrogen, was forged in such an explosion. But at the center, where the core collapsed, a black hole remains, silent, invisible, warping space-time around it so severely that light itself cannot escape. This is a stellar mass black hole, typically between 3 and 20 times the mass of the Sun. But there are other ways to make black holes. Supermassive black holes, millions to billions of times the Sun's mass, lurk at the centers of most galaxies, including our own Milky Way. How they formed is still not entirely clear. Perhaps they grew by consuming gas and stars over billions of years. Perhaps they formed directly from the collapse of massive gas clouds in the early universe. Likely it's a combination of both. There may also be primordial black holes, formed in the first moments after the Big Bang, from density fluctuations in the early universe. These would range from microscopic to stellar mass. We haven't confirmed they exist yet, but they're a possibility. And at the other extreme, there might be intermediate mass black holes, hundreds to thousands of solar masses, perhaps formed from the mergers of smaller black holes or from very massive stars that existed only in the early universe. Black holes come in many sizes, but they all share the same defining feature: an event horizon, a boundary beyond which nothing can return. The event horizon is not a physical surface. It's not made of matter. You couldn't touch it or bounce off it. It's simply a boundary in space-time, a point of no return. The definition is precise. The event horizon is the boundary where the escape velocity equals the speed of light. Escape velocity is the speed you need to reach to escape from a gravitational field. On Earth, it's about 11 kilometers per second. Launch a rocket at this speed, and it can leave Earth entirely, never to return. For the Sun, escape velocity at the surface is about 618 kilometers per second. For a white dwarf, a dense stellar remnant, it might be several thousand kilometers per second. For a neutron star, it can reach a significant fraction of the speed of light. But for a black hole, at the event horizon, the escape velocity reaches exactly the speed of light, 299,792 kilometers per second. And since nothing can travel faster than light, not matter, not energy, not information, nothing that crosses the event horizon can ever escape. The size of the event horizon depends on the black hole's mass. The radius is called the Schwarzschild radius, named after Karl Schwarzschild, who derived the exact solution to Einstein's equations for a non-rotating black hole in 1916, just months after Einstein published general relativity. The formula is simple. R equals 2gm over c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. Compress the Sun to a sphere 6 kilometers across, and it would become a black hole. For a black hole with 10 solar masses, typical for stellar mass black holes, the radius is about 30 kilometers, about the size of a large city. For a supermassive black hole with 1 billion solar masses, like the one at the center of the M87 galaxy, which we photographed in 2019, the Schwarzschild radius is about 3 billion kilometers, roughly 20 times the distance from the Sun to Earth, large enough to swallow our entire solar system out to Uranus. Here's something counterintuitive. The larger the black hole, the lower the density at the event horizon. A stellar mass black hole has an incredibly high average density, far denser than a neutron star. But a supermassive black hole can have an average density lower than water. The M87 black hole, despite containing 6.5 billion times the Sun's mass, has an average density about that of air at sea level. This is because volume increases with the cube of radius, while mass increases linearly. Make a black hole 1,000 times more massive, and its radius increases by 1,000 times, but its volume increases by 1 billion times. The density drops accordingly. But density is a somewhat misleading concept for a black hole, because all the mass is concentrated at the singularity at the center. The event horizon itself is just empty space-time, curved space-time to be sure, but there's nothing there. No matter, no substance. If you were falling toward a black hole and crossed the event horizon, you wouldn't feel anything special at that moment. There's no barrier, no wall, Locally, space-time seems normal. You'd pass through the horizon without noticing. But you'd be doomed. From your perspective, falling inward, time continues normally. You'd cross the horizon in a finite amount of time, minutes, seconds, or fractions of a second, depending on the size of the black hole and your trajectory. But from the perspective of someone watching from a safe distance outside, something very different happens. As you approach the horizon, time dilation becomes extreme. Your clock, as seen by the distant observer, runs slower and slower. The light you emit becomes redshifted, stretched to longer, redder wavelengths, and dimmer. You appear to slow down, approaching the horizon asymptotically, never quite reaching it. The last photons you emit, the last light to escape from just above the horizon, takes longer and longer to reach the distant observer. To the outside universe, you freeze at the event horizon, your image fading and reddening as the photons stretch and weaken until you vanish from view entirely. Time, from the distant observer's perspective, stops at the horizon. But from your perspective, you've long since crossed the horizon and fallen toward the singularity. This is one of the deep paradoxes of black holes. Different observers experience time differently. There's no universal now. Your now and the distant observer's now diverge completely at the event horizon. Once you've crossed, there's no turning back. Not because you lack a powerful enough rocket, though you'd need infinite power to escape, which is impossible, but because the structure of space-time itself forbids it. Inside the horizon, all paths lead inward. Every trajectory, no matter which direction you try to move, takes you closer to the singularity. You can no more escape the singularity than you can escape tomorrow. Time and space, in a sense, swap roles inside the event horizon. Outside, you can move freely in space, but are pulled inexorably forward in time. Inside, you can move freely in time, at least conceptually, but are pulled inexorably inward in space, toward the singularity. The singularity isn't a place in space. It's a moment in time, an unavoidable moment in your future. You will reach it, and when you do, that will be the end. So, what happens inside the event horizon? In that forbidden region we can never observe, never escape, never send a signal back from. General relativity gives us predictions, but we must remember these are extrapolations. We have no direct evidence. We can't test them. We can only trust the mathematics of Einstein's equations. The first thing to understand is that crossing the horizon, while a momentous event from an outside perspective, isn't necessarily dramatic for you, the infalling observer, at least not initially. For a supermassive black hole, the horizon can be so large and the curvature of space-time so gradual there that you'd cross it without feeling anything unusual. Locally, space-time seems flat. The laws of physics appear normal. You wouldn't even know you'd crossed the point of no return until you tried and failed to send a signal back out. But for a stellar mass black hole, the story is different. The horizon is small, the curvature steep, and tidal forces, differential gravitational pull, become extreme. Imagine you're falling in feet first. Your feet are closer to the black hole than your head, so they experience stronger gravity. This difference in gravitational pull stretches you vertically. At the same time, the gravitational field pulls everything toward the center, so you're compressed horizontally, squeezed from the sides. This is called spaghettification, and it's exactly as unpleasant as it sounds. You'd be stretched and squeezed, pulled into a long, thin strand, like a piece of spaghetti. For a stellar mass black hole, spaghettification would occur before you even reach the event horizon, tearing you apart at the molecular level. For a supermassive black hole, you might pass through the horizon intact, succumbing to tidal forces only as you approach the singularity deep inside. But let's assume, for the sake of exploration, that you've crossed the horizon of a supermassive black hole intact. What do you see? What do you experience? Looking outward, back toward the universe you left, you'd see something strange. Light from the outside universe would be blue-shifted, compressed to shorter wavelengths, and appear to speed up. Events that would take eons outside happen in moments from your perspective. The universe's distant future would play out before your eyes as you fall. Or so the mathematics suggests. In practice, the light would be so blue-shifted that it would shift into X-rays and gamma rays, invisible and deadly. Looking inward toward the singularity, you'd see, well, we don't know. The equations become ambiguous. Some solutions suggest you'd see infinite curvature, infinite density. Others suggest more exotic structures. The singularity, according to general relativity, is a point where space-time curvature becomes infinite, where density becomes infinite, where the equations break down and stop making predictions. At the singularity, general relativity fails. It reaches the edge of its domain of applicability. To understand what really happens there, we'd need a theory of quantum gravity, a theory that unifies general relativity with quantum mechanics. And we don't have one yet. So, the singularity remains a mystery. Is it truly a point of infinite density? Or does quantum mechanics intervene at some small but finite scale, preventing the collapse from reaching true infinity? Some theories suggest that quantum effects might create a bounce where the collapsing matter rebounds, creating a new expanding region, perhaps even a new universe, on the other side. Others suggest that the singularity is real, but surrounded by a horizon of quantum foam, where space-time becomes probabilistic and uncertain at the smallest scales. We don't know. And from outside, we can never know. The event horizon hides the singularity from view, ensuring that whatever happens there, however strange, however violent, remains causally disconnected from the outside universe. This is the cosmic censorship hypothesis, that singularities are always hidden behind event horizons, never naked and exposed to the universe. It's not proven, but most physicists believe it's true. The universe, it seems, has a modesty about its infinities. But whether the singularity is truly infinite or merely very extreme, the outcome for you is the same. You're destroyed, your information scrambled, your atoms crushed out of recognizable existence. Or are they? Black holes seem like perfect destroyers of information. Whatever falls in is lost forever, hidden behind the event horizon, crushed at the singularity. The universe forgets what fell in, retaining only the black hole's mass, charge, and spin. 3 numbers. Everything else, every detail about the matter that formed the black hole or fell into it, is erased. Or is it? This leads to one of the deepest paradoxes in theoretical physics, the black hole information paradox. In quantum mechanics, information is never truly destroyed. The state of a system evolves deterministically according to quantum laws. If you know the state at one time, you can, in principle, calculate the state at any other time, forward or backward. Information is conserved. But black holes seem to violate this principle. Throw a book into a black hole, and the information in the book, the arrangement of atoms, the text on the pages, seems to disappear from the universe. Only mass, charge, and spin remain. This bothered physicists for decades. Does the information really vanish? If so, quantum mechanics is violated, and our understanding of physics is incomplete. In 1974, Stephen Hawking discovered something surprising. Black holes aren't entirely black. They emit radiation. This radiation, now called Hawking radiation, arises from quantum effects near the event horizon. In quantum field theory, empty space isn't truly empty. Virtual particle-antiparticle pairs constantly pop into existence and annihilate each other, borrowing energy from the vacuum for brief moments. Near the event horizon, one member of a virtual pair can fall into the black hole while the other escapes. From the outside perspective, it looks like the black hole emitted a particle. This emission comes at a cost. The black hole loses mass. Each particle that escapes carries away a tiny bit of energy, and by Einstein's E equals mc squared, that energy corresponds to mass. The black hole shrinks. Over time, immense time, the black hole evaporates completely. For a stellar mass black hole, this takes about 10 to the 67 years, far longer than the current age of the universe, 10 to the 10 years. For a supermassive black hole, it takes even longer. But eventually, given enough time, the black hole disappears, leaving only the Hawking radiation, a bath of thermal photons and particles. And here's the problem. Hawking radiation, as originally calculated, is thermal. It's random. It carries no information about what fell into the black hole. It's like the heat from a fire. It tells you the fire is hot, but not what was burned. If the black hole evaporates completely and the radiation carries no information, then the information that fell in is truly lost. Quantum mechanics is violated. This is the information paradox. For decades, physicists debated this. Some argued that information is destroyed and quantum mechanics must be modified. Others insisted that information must be preserved somehow, encoded in the Hawking radiation in subtle ways we didn't yet understand. Hawking himself initially believed information was destroyed, but later changed his mind, conceding that information might be preserved in correlations within the radiation that are too subtle to detect easily. Recent developments suggest the information isn't lost. It may be encoded in the quantum entanglement between the Hawking radiation particles, or stored in subtle correlations at the event horizon, or encoded in structures we call soft hair, quantum states near the horizon that can store information. The leading candidate for resolving the paradox is the idea that the event horizon has more structure than classical general relativity suggests. Quantum mechanics gives the horizon a kind of macroscopic texture, and this texture can encode information. There's also a deep connection between black holes and thermodynamics. A black hole has entropy, a measure of disorder, or the number of possible microscopic states. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is strange. Normally, entropy is an extensive property. It scales with volume. But for black holes, it scales with surface area. This led to the holographic principle, the idea that all the information contained within a volume of space can be encoded on the boundary of that volume, like a hologram. The three-dimensional world might be, in some sense, a projection from a two-dimensional surface. These ideas are at the cutting edge of theoretical physics. They're not fully understood yet. Black holes continue to challenge our understanding, revealing connections between gravity, quantum mechanics, thermodynamics, and information theory that we're only beginning to grasp. Black holes are laboratories for testing our deepest theories. They sit at the intersection of the very large, gravity, space-time, cosmology, and the very small, quantum mechanics, particles, fields. Understanding them fully requires unifying these domains, a task that has eluded physicists for a century. For a long time, black holes were purely theoretical. They were solutions to Einstein's equations, but whether they existed in nature was unknown. Einstein himself doubted they were real. But evidence accumulated slowly, and by the late 20th century, their existence was beyond reasonable doubt. The first strong candidate was Cygnus X1, discovered in 1964 as a powerful X-ray source. In 1971, astronomers identified it with a visible star, a blue supergiant in a binary system. The star was orbiting something invisible and massive. By tracking the star's motion, astronomers determined the invisible companion had a mass of about 15 times the Sun, far too massive to be a neutron star, which can't exceed about 3 solar masses. It had to be a black hole. But the evidence was indirect. We couldn't see the black hole itself, only its effects on its companion star. The clinching evidence came from the material spiraling into the black hole. As gas from the companion star falls toward the black hole, it forms an accretion disk, a swirling disk of superheated matter. Friction in the disk heats the gas to millions of degrees, causing it to emit X-rays. We can't see the black hole, but we can see the glow of the accretion disk and the X-rays from the infalling matter. It's like seeing a whirlpool by watching the water spiral down the drain. Dozens of X-ray binaries, like Cygnus X1, have been found since, confirming that stellar mass black holes are common. Supermassive black holes were discovered by observing the motions of stars near galactic centers. At the center of the Milky Way is a radio source called Sagittarius A star. Since the 1990s, astronomers have tracked individual stars orbiting very close to Sagittarius A star. These stars move incredibly fast. One star, S2, reaches speeds of 7,650 kilometers per second, nearly 3% of the speed of light, during its closest approach. By watching these orbits over decades, astronomers calculated the mass of the invisible object they're orbiting, about 4 million solar masses, concentrated in a region smaller than the solar system. There's no known object other than a black hole that can be so massive and so compact. The evidence is overwhelming. For this work, Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize in Physics. Roger Penrose, who proved mathematically that singularities must form in gravitational collapse, shared the prize with them. But the most direct evidence came in 2015, when the LIGO detectors in the United States detected gravitational waves, ripples in spacetime, from the merger of two black holes. The signal was unmistakable. Two black holes, each about 30 solar masses, spiraling together, merging into a single black hole, and releasing 3 solar masses worth of energy in the form of gravitational waves in a fraction of a second. The waveform matched the predictions of general relativity perfectly. The frequency, amplitude, and duration of the signal told us the masses, spins, and the distance of the black holes. It was a triumph of theory and experiment. Since then, LIGO and its partner detectors have detected dozens more black hole mergers, confirming that black holes are common, that they merge regularly, and that Einstein's equations describe their behavior with exquisite precision. And then, in 2019, came the image. The Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized telescope, captured an image of the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image showed exactly what theory predicted. A dark shadow, the black hole's event horizon, surrounded by a bright ring of glowing gas in the accretion disk. The shadow was slightly larger than the event horizon itself, because light from behind the black hole is bent around it by the extreme gravity, creating a larger silhouette. But the size, shape, and brightness matched predictions. It was the first direct visual evidence of a black hole's event horizon, a confirmation that these objects, once thought too strange to exist, are real features of our universe. Black holes are no longer theoretical curiosities. They're observed facts, confirmed by multiple independent lines of evidence. They're as real as stars, planets, and galaxies. And they're everywhere. Our galaxy likely contains tens of millions of stellar mass black holes, the remnants of massive stars. Every large galaxy has a supermassive black hole at its center. They're fundamental components of the universe's structure. Black holes are places where the universe ends, or at least where our understanding ends. At the event horizon, time and space exchange roles. Beyond the horizon, all paths lead to the singularity, and nothing that enters can escape. At the singularity itself, density becomes infinite, curvature becomes infinite, and the equations we use to describe reality break down. We stand at the edge of understanding, staring into the abyss, and the abyss offers no answers, only questions. What happens at the singularity? We don't know. General relativity stops working there. We need a theory of quantum gravity, and we don't have one yet. Is information destroyed, or is it preserved in ways we don't yet understand? The paradox remains unsolved, though physicists are making progress. Are there other types of singularities? Other ways space-time can tear or fold that we haven't imagined yet? Possibly. And perhaps most tantalizing, could the singularity at the center of a black hole connect to something else? Could it be a bridge to another region of space, or even another universe entirely? These are questions we may never answer. The event horizon is a one-way membrane. We can send probes, even people, into a black hole, but we can never retrieve information about what they find inside. And perhaps that's okay. The universe is not obligated to make itself comprehensible to us. Mystery is not a failure of science. It's a feature of reality. Some questions may be unanswerable, not because we're not clever enough, but because the universe has placed them beyond the boundary of the knowable. Black holes remind us of the limits of knowledge. They humble us. They show us that for all our progress, for all our equations and telescopes and theories, there are still edges we cannot cross, questions we cannot answer. And there's something beautiful in that, something profound. We live in a universe strange enough to contain black holes, strange enough that space-time can tear and collapse, strange enough that the speed of light is a limit, that time is relative, that gravity is not a force, but the curvature of space itself. For now, as you drift towards sleep, imagine floating in space, far from any black hole, safely distant, but near enough to see one silhouetted against a field of stars. You can't see the black hole itself. It's a circle of perfect darkness, but around it, you see the distortion it creates, starlight bent into arcs and rings, the background stars smeared and duplicated by the extreme curvature of space-time. And if there's an accretion disk, you might see it glowing, a thin ring of light encircling the darkness, matter spiraling inward, releasing its final photons before crossing the horizon and vanishing forever. It's beautiful and terrifying, an object so dense, so extreme, that it warps the fabric of reality itself. A place where time slows to a stop, where space folds inward, where the laws of physics as we know them cease to apply. But you're safe here, watching from a distance. The black hole cannot reach you. It sits in its own pocket of space-time, isolated, patient, eternal, or nearly so. And you are here, now, in this moment, held by the gentle gravity of Earth, far from any extreme curvature, far from any singularity. Rest, knowing that the universe is stranger and more wonderful than we can fully comprehend. Rest, knowing that the mystery is not something to fear, but something to appreciate. The black holes are out there, scattered across the cosmos, marking the places where stars died and gravity won. They'll be there for trillions of years, long after the last stars burn out, slowly evaporating through Hawking radiation, returning their mass to the universe, one quantum at a time. But that's far in the future. For now, they remain silent, dark, patient, at the edge of everything we know.